Hey, Mr. McLaren here. So we are going to be going over how to use the simulation. I'm going to be kind of walking you through it, and then you could watch this video and just pause it to do the work and kind of follow along, is what I'm thinking. So let's see. If I click on this. Yeah, it's kind of weird. Some of this info, I want to walk you through this because the S&P interval is kind of weird. It's not something worth focusing on. Basically, different waves travel through the Earth differently. So some of them go fast, some of them go slow, kind of like how with lightning you can hear thunder and see the lightning, and then the difference in when you see the light and hear the lightning should tell you roughly how far away it is. That's basically what we're doing here with the earthquakes. There's like two different waves that go through the earth. One goes faster, one goes slower. And you look at the difference in time, and that should tell you how far away the earthquake is. So if we're looking here, let's go down to LA or near LA. If we click on that, then we've got some earthquake that's occurred, and we've got these different readouts on these seismometers. This is basically just measuring the earth shaking. It's quite literally like just like a needle on something, and if the machine shakes, it shakes. So like they're very, very, and that's the main idea. They're very simple machines, and if you have an earthquake, it's gonna make it go up and down, right? So we have the first wave come and then the second wave. We're trying to figure out how much time is between those. So it goes from here to there. That looks like it's somewhere between 40 and 50, maybe a little bit closer to 50. So like that. If you get them wrong, it tells you that you're wrong. If you get it right, it gives you the check and lets you move on, basically. So I'm going to challenge you to try and do this one, next one on your own. So you can pause the video now and do that, or you could watch me and do it with me. So 0 to, it looks like a little bit more than 60. So maybe there. Yep. Hey, we're doing some graphing. We're recognizing some graphing skills. Woo! I haven't done this in a while. um, so we've got our time here. Also, I should have probably gone over the axes of time and amplitude. So we're looking at difference in time, and we're seeing these peaks or these spikes, and we're looking at when they happen. They've labeled them for us. So that's kind of nice. So we're going from 0 to, it looks like just after 70. It's like 71. Yep. And that should be good for that. Okay, so now we know the amount of time between the first wave, which is kind of like your lightning, and then the second wave, which is the thunder. And so we should be able to, in our analogy, so we should be able to figure out how far away um, this earthquake was. So if it took this amount of time, it should be this distance. So it looks like from LA, our earthquake is about 450. Yeah. Again, you can go ahead and try and do the other two or watch with me at this point. So yeah, you could pause now and try it. Okay, so 60, looks like that's 600 pretty much exactly. That's easy. And then 70 is pretty much 700. Okay, nice, easy math. It's nice when the simulation gives us that, right? Um, so it looks to me like as this goes up, that is also going up. So it's like a linear relationship. Makes sense. The further something is away, the longer this time is going to be between the fast and the slow wave. So I think that we're saying is this one's getting bigger, that one's getting bigger. Yeah. Okay, so that looks like now we know that it's a certain distance away from LA. So you could draw out a circle from that origin, and all points on that circle are that distance. So if we were just looking at LA, they might think the earthquake was out here or down there, right? But then Arizona says, whoa, 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 whoa. It's not over here because it was pretty far away from us. It's somewhere on this green line. And so LA and Arizona, if it's just the two of them talking, they might think it's here or there. But Roseburg would say that's too far away. Like it should be only 700 meters away from us. So the earthquake originated around there. That's the main idea, honestly. The scientists, they look at when these things come in, and they're able to figure out how far away these things are that happen from them, and they just draw the circles and find where the circles Match. Um, this part is a little bit more about the magnitude of the earthquake. This is less important for me, but it's worth talking about. So we can obviously, like, bigger earthquakes are gonna have bigger amplitudes, but if they go further, they get smaller over time. So it's kind of weird for this. What is the amplitude of our S wave here? It was somewhere between 250 and 300. I think it's that. Okay, cool. And then the amplitude here was, and again, you can try and do this on your own. I would recommend that. It's good to practice some of our math skills here. 0 to, it looks like just under 100 maybe. I think that's the 100 line right there. So I think it's 90. Yep. And then this looks like it's pretty much at the 50. Okay. So this, honestly, this I didn't get the first time I did this. They're basically trying to show the relationship between the distance and the amplitude. So if you click on this to that, and then this to that, this to that, this tells you the magnitude of the earthquake or how powerful it was. Um, Basically, this one that was really farther away, or this one was really close, had a bigger wave, right? So by drawing these lines out, it kind of says, like, the further away ones, it's okay that they're smaller. Because if you had something that was really far away, it's okay that it's a really small amplitude, and that it should match up with the scale. I honestly didn't know how the Richter scale worked before this. I did the simulation. Now I do. It's pretty cool. Um, Again, the main idea is I'm just trying to get you to understand how someone tries to find an origin of an earthquake, just so you can kind of see this. A 7.0 magnitude, I actually know what they're talking about here, and I'm familiar because I'm from these places, but that's a pretty big earthquake. Um, it's like a very big one. And that's okay if you don't know that. This actually, oh no, this isn't where I'm from. The Loma Prieta, I actually grew up like going to Loma Prieta Elementary School. Like, the elementary school that I went to was on the fault line of this earthquake, and it was pretty close to the origin actually as well, because it's named Loma Prieta. Yay, local pride of my earthquake area. So yeah, that's basically how you do the simulation here. Then you're going to summarize down below. I would say something like, they look at when an earthquake makes a spike on the seismometer or the machine, and then they compare those different machines at different places, um, to what they call it is triangulation, or making a triangle to try and find that one point where it originated. You can go into as much detail as you would like. You can look back at that simulation, use some of the words that they were using, but the main idea here is that they look at the seismometers and they compare, you know, the size of the amplitudes and the amount of time between that first wave and that second wave, or the, like, thunder and lightning. Okay, awesome, cool. I'll see you guys in class.